Hello, I'm Marco Fainello. I have over 30 years of experience in designing and integrating, producing, testing, and developing cars with the most known manufacturers in the world, like Ferrari, Lamborghini, Porsche, Maserati, Alfa, Fiat, and others. Since 5 years, I am Chief Technical Officer of Danisi Engineering, a company based in Italy, but working with many different international customers in order to supply services of design, integration, production of prototypes, supply system for chassis, suspensions, and so on. One peculiarity of Danisi Engineering is that since its creation 26 years ago, has been using simulation, simulators, hardware and software in the loop, human in the loop, in order to support its process of designing vehicles and for integration of different systems, mechanical and electronic, problem solving and support the tuning and sign-offs of the car. With this long experience, Danisi Engineering is able and is supplying support to many OEMs and tier one suppliers in order to help them to use, to improve, to optimize their methodologies in order to achieve better results, better product in shorter time and with less cost. Mainly in integrating new technology and understanding how the new technology impact can influence the product and how it can be used in order to give them a better position in the market with their own customers. We supply support, training, design, testing, truck testing, road testing to our customers, to show them how to use their own simulator or to use our simulator that we rent in order to provide the services. Or we use our own simulators in order to provide the final result, the work packages that are required by the different situations. Today, one of our senior engineers, Federico Ravera, will explain you some example or how we use simulation and simulators in order to optimize handling and ride comfort of the vehicles. One of the paramount importance of our methodologies is to make sure that we have a good validation between the simulations and the real results. We dedicate a lot of effort and time in order to validate our methodologies before we really use it and apply with our customers. This is because we need to be sure that all the results and all the choices we made based on our methodology based on simulation and simulators are relevant and can be used in order to create the prototypes and make sure that the final product is satisfying the requirements. Therefore, we have many methodologies and validations that are using simulation for benchmarking, for design evaluation, for choices and target setting for the products, for failure mode analysis, for safety analysis, applied to different systems, suspensions, control, powertrain, traction, hybrid, electric powertrain, driving assistance system, ADAS, and so on. Depending on the requirements of different customers, we are able to provide different level of assistance, from the turnkey work package project where we do everything in the car according to the requirement of the customer, up to the single system, single component support or simulation testing, simulator testing, road and truck testing, or simply training in order to help our customer to speed up the process of learning how to use these tools in order to improve their own process. So I leave the word to Federico Ravera that will give you some examples on the application of our methodologies, and I hope you find it interesting. Thank you.
Hello everybody. Thank you, Marco, for the introduction. My name is Federico Ravera. I'm a senior simulation engineer in the Advanced Vehicle Dynamic department of Danisi Engineering, and I've been working in this department for more than 6 years. Today, I will present you our integrated methodology for ride and handling development. Our vehicle development methodology in Danisi Engineering is based on subjective and objective targets. The targets are usually set during a benchmarking activity in which several competitors' vehicles are assessed and measured. This helps in the definition of the goals for a vehicle which is under development. The first important part regards subjective targets, which are, of course, directly impacting the occupant's perception of vehicle performances. From subjective targets, then, objective ones are obtained. The idea here is to set the objective targets in a way that when achieving them, also the subjective ones are satisfied. This sort of target setting activity is done both for ride and for handling performances, and it's kind of the key criteria that guides vehicle development. A fundamental role is played by our innovative blending methodology. We consider this methodology to be a step forward compared to traditional approaches to simulation and virtual models. In fact, in the past, vehicle models were usually created only after the availability of new vehicle prototypes, leading to the creation of a so-called digital twin. As a consequence, simulation played a very marginal role, especially in the definition of the first prototypes and on very important architectural choices which are usually made very early in the project. In Danisi Engineering, we worked on our methodology and know-how really in order to be able to build a reliable vehicle model in advance, even during the first prototype design phase. We call this vehicle model a virtual prototype. We can say that in this way, simulations becomes a part of a blending methodology in which all the main parts of our engineering process you can see summarized in the circle here in the slide. All these main parts are blended together in order to creating prototypes with higher level of significance. The key idea behind this approach is to anticipate part of the development of the new car using simulation and its integration with our other engineering areas. In this way, the prototypes and road testing activities are reduced and especially focused on higher quality activities. This helps in reducing times, cost, and of course at the end obtaining better cars. The availability of a reliable virtual prototype from early stage allows us to focus on subjective and objective targets since the beginning of a project. Here you can see our development loop in which there is a strong interaction between different engineering areas and all the main vehicle suspension characteristics and vehicle characteristics are integrated into the vehicle model. This allows us to check the target achieving for both objective and subjective parts. A development loop is then required until the targets are achieved. And the benefit from this kind of approach is that the vehicle and systems design is driven by vehicle targets since the beginning of the project. Handling and ride conflicts are also addressed really in advance, leading to the best possible optimization between them. At the end, we will have a final vehicle with higher quality and also reduced time and costs. You are welcome to join me here in VECTORINO in the heavy department. In this department, we also have a road testing team who is managing all the road testing activities from handling to ride, both for objective and subjective evaluation. For example, here we are instrumenting a vehicle for an handling characterization. So here you can see a colleague who is working on the instrumentation. I can guide you through all the instruments we are mounting on the vehicle. Starting from the front of the car, in which we have this optical sensor that is used for measuring side slip angle and vehicle velocities. And then we can go in the back of the car. Here we have the other important pieces of the instrumentation. For example, there you can see an IMU, which is used for accelerations and rotational velocity measurement. And here all the electronics that help us to log all the required channels. The same road testing team is also working on the right side. So we have a similar sort of instrumentation for measuring all the required channels for objective ride analysis. And also we have the expertise for subjective ride evaluations. In Danisi Engineering, we do ride comfort evaluation using also simulations and driving simulators. For a trustable result in this topic, we focus on two main pillars that I will illustrate you in the following. The first one is related to a valid simulation results that is obtained first of all using trustable vehicle models. And in Danisi Engineering, we use a variety of vehicle models, starting from the first model in early project phase to the most advanced ones, like multi-body models. We also validate the vehicle models both for handling and ride comfort evaluation, which is of course really important. Another important aspect is related to the tire model, that for ride simulations is especially important. And the tire model should be accurate for this kind of evaluation. A simple handling tire model is not enough. The other important pillar for ride simulation is to have validated acceleration on the cockpit of the driving simulator. In Danisi Engineering, we developed a methodology for reaching such a goal. As you can see from the pictures here, we conducted a measurement campaign in which we mounted accelerometers on specific points of the cockpit. Then, thanks to our methodology, we validated the accelerations in these points against simulation results and track measurements. This methodology allows us to compensate for the DIM and cockpit transfer function. When dealing with subjective handling evaluation on a driving simulator, our attention goes to making sure that the dynamic simulator reproduces in the, let's say, best possible way the vehicle dynamics. We achieve this goal by using a strong approach to motion cueing tuning. The motion cueing is, in dynamic simulator, is the algorithm that controls the motion of the dynamic platform in function of the simulated motion of the vehicle model. Here in Danisi Engineering, since the installation of our team in 2016, we worked for building an approach that gave us comparable subjective evaluation for the same vehicle, both driven on the simulator and in physical world. We validated this method on several vehicles, of which we had both the physical car and the virtual model. Thanks to this approach, we are now able to apply our motion cueing tuning process very early, even since the start of the physical prototype design phase, ensuring in this way that subjective evaluation on the DIM of virtual mules are trustable. The other important point when dealing with subjective feeling on driving simulators is the driver itself. In fact, the approach should be a little bit different compared to physical world testing. In Danisi Engineering, we develop a standard approach for the so-called adaptation phase. This is making us sure that the subjective evaluation that our professional drivers give us on the driving simulators is correlated to the one that they give in physical world testing. We also suggest this adaptation phase to all new customer drivers that are coming to visit us here in AVD Center. We will now see some examples of our methodology applied to some case studies. The first one regards the optimization of ride and handling characteristics on an hypercar. In this case, we applied our development loop for defining the spring stiffness values. We started from a benchmarking activity for the first definition of the number of frequencies, and then we checked how our first hypothesis was impacting on objective and subjective targets, both for ride and handling characteristics. Actually, we found out that the values of natural frequency that we set at the beginning of the project were creating some problems on handling side. So we had to do several loops of optimization looking for the best compromise between ride and handling. This optimization process has been possible only with this integrated approach using simulation. Using our methodology, we have been able to perform failure model analysis on the steering systems using our static simulator and steering bench. The steering, mechanical systems and control logics were integrated into the simulation loop using hardware in the loop. We also used our HILDIS bench, which allows to have the real steering systems in the simulation loop. This setup, together with our methodology for simulation, allowed us to perform this safety test before the first prototype was built. In this case, we connected the ECU of the steering system and we injected some fault which led to abnormal values of steering torque. The reaction of the vehicle was then assessed by a professional driver in order to evaluate if it was still safe enough, even when a failure or a fault occurs. The same approach was previously validated using an existing vehicle, giving us confidence on the subjective results obtained in simulation. For the same steering system, we perform mechanical validation tests using simulation and hardware in the loop. In the video, you can see our HILDIS bench that was invented and produced by us. This HILDIS bench allows to integrate the complete real steering system in the simulation loop, also for driver in the loop activities. This is something quite unique in this simulation world. In this case, we use the bench for a series of automated tests meant to validate mechanical performances of the steering system. We also created a steering robot that moves the steering rack in accordance to the test case. The sensors in the HILDIS bench were then used for measuring loads on the rack. If you're interested in integrated HILDIS into your simulation loop, we are of course happy to help you. The torque vectoring system exploits different left-right wheel torques in order to influence the vehicle dynamics. As you can see from the picture on the right, having a different level of torque on one side of a vehicle compared to the other side creates a yaw moment around the center of gravity. This is actually changing the dynamics behavior of the vehicle, meaning that using this effect we can improve its characteristics both in steady states and transient conditions. This effect is very common nowadays because it perfectly fits on hybrid and electric vehicles, which may have independent control of a torque on a single wheel. In Danisi Engineering, we developed a torque vectoring control system, and we applied it to an hypercar with two independent motors on the front axle. Unfortunately, the same principle which is behind the torque vectoring effect can create some undesired effect in some conditions. In fact, having different left-right torques on the front axle may create steering wheel torque reactions and steering torques perturbances. This is called torque steer. This effect is influenced mainly by a suspension metric, the lateral distance between the steering axis and the wheel center, the so-called hub offset. The higher the hub offset is, the more likely the torque steer is. But we have to say that the correct value of hub offset is a sort of trade-off with other suspension characteristics, and it's also strongly depending on the tuning of the torque vectoring systems. Usually higher control performances create higher torque steer effects.
When we approached the integration of our torque vectoring control for this vehicle, we had to understand from the beginning which was the target value of hub offset in order to reach the best compromise between torque vectoring performances and acceptably low steering torque effects. We started by tuning the torque vectoring system on our simulator in order to reach our targets that we set at the beginning of the project. Then we made some loops of optimization of the suspension design in which we changed the hub offset value until our professional drivers evaluate that the torque steer was acceptably low. In this way, we found the target value of the hub offset. Without this approach, it would have been impossible to design the suspension in the correct way since the beginning, leading to a series of compromises on performances.
This use case is relative to the obstacle avoidance system. This kind of system is an aid to the driver in emergency situations in which an obstacle in front of the vehicle is detected and an avoidance maneuver is required. The obstacle avoidance system involves several sensors like a radar system and camera and others. We integrated these sensors in our simulator environment using hardware in the loop and software in the loop. And this allowed us to reproduce and validate the obstacle avoidance maneuver in simulation. Once the simulated scenario is created, the development process of ADAS and autonomous driving system is speed up, since we can easily try several times the same scenario in a very repeatable way, something which is not possible in the real world. This is really helping in reducing physical testing with a strong reduction on times and costs.
We reached the conclusions of this presentation, and we saw thanks to our strong methodological approach, we are able to integrate simulation and other engineering process since very early phases of the project. This is all aimed to reduce time and cost spent in physical testing, but focusing on higher quality activities. We can say at the end that our approach to ride and handling development is based on the combination of simulation and prototypation, leading to the so-called simulotipation. Thank you for the attention.